Imagine you're spinning up a fresh, pristine Docker container. You load your application, get your API key sorted out, and the service just starts humming perfectly.
Right. Everything is just locked in and ready to go.
Exactly. It handles this complex user request flawlessly. But the moment that single transaction finishes, the orchestrator just ruthlessly kills the container.
Wipes it completely off the memory.
Yeah. And then the next time that exact same user pings your service, a brand new, completely blank container spins up. I mean, it has zero idea who the user is or what they just asked for, like 5 seconds ago.
Which is, from an infrastructure perspective, just a wildly inefficient way to run a continuous server.
Oh, absolutely.
You just burn through your compute budget managing all that overhead.
You really would. But here's the thing. For you, the software engineer listening right now, staring at your IDE and building with large language models, this is your default reality.
Yeah, that stateless ephemeral container is basically what you're building when you create an AI agent without memory.
So welcome to a new deep dive. We're dimming the lights tonight and tuning out the noise to focus on just one single critical mission. We are decoding the mechanics of continuity in agentic AI.
And we're working from a really extensive set of technical notes today. They cover LLM memory systems, agentic architecture, all of that.
Yeah, the sources map out this really fascinating transition in how we build.
Right, because we look at the broader engineering landscape right now, we've solved a lot of the core agentic primitives.
Let's contextualize that a bit. I mean, we have embeddings, right? They map language into high-dimensional semantic space.
Exactly.
We have robust multi-agent frameworks. We've got function calling, which means, our AI can autonomously trigger webhooks or query APIs, even execute Python code.
Yeah, and we even have decent planning modules now for breaking down those really high-level tasks into, manageable subtasks.
Right, so we have the engine, the transmission, the wheels, all of it.
But, and this is what the sources argue so strongly, all of those capabilities are essentially stranded without a memory layer.
Okay, let's unpack this. Because as software engineers, I think we're a bit spoiled by deterministic systems,
Oh, totally. We take traditional database state completely for granted.
Exactly. Like, if a user sets their app to dark mode, I just write a Boolean to a Postgres database. Done. State management is simple, it's static, it's reliable.
But reading through these nodes, giving an artificial intelligence memory isn't just, a basic CRU operation. It's an entirely different paradigm.
Right. It's not just updating a row in a table.
No, not at all. The shift in thinking requires moving away from just data storage and really moving toward data relevance.
Okay, so to understand complex memory, the sources say we have to look at the baseline constraint first, right? The context window.
Yeah, we have to examine the mechanics of that window. It functions as the agent's short-term memory.
Like it's active processing RAM.
Exactly. And it's characterized by this brutal binary. Within the limits of that window, the model has flawless, crystalline recall of every single token.
But the moment you exceed that token limit, you hit a cliff edge.
Total amnesia for anything outside the window. Yeah. Just gone.
Wow. And we should probably explore the underlying math of why that boundary is so rigid. Because I know a lot of developers look at Moore's Law and think, well, compute just gets cheaper.
Right. They think, let's just scale the context window. Give the agent a 10 million token window, pass it the entire database on every prompt, and problem solved. No need for long-term memory.
I've definitely seen teams try that brute force approach, but the hardware reality hits you really fast.
Oh, yeah. The self-attention mechanism inside transformer models, it scales quadratically.
So wait, break that down for the listener.
The math is just unforgiving. If you double the size of the context window, you don't double the compute required, you quadruple it. Yeah, because every single new token you feed into the model has to calculate its relationship, its attention weight, against every single previous token in the sequence.
So if you pass like 1 million tokens into the window.
That is 1 trillion relationship calculations happening matrix by matrix before the model even generates a single word.
That's insane. So the latency just skyrockets.
Skyrockets. The GPU memory requirements become astronomical, and honestly, your cost per API call becomes completely unviable for a production application.
So basically, physics and economics force our hand here. We just cannot rely on the short-term RAM of the context window indefinitely.
Right. We are required to build a permanent storage layer.
Yeah.
But looking at the source material is not as simple as just dumping raw text into a database.
Yeah, the notes break long-term memory into 2 really distinct branches, episodic memory and semantic memory.
And that distinction completely dictates how you structure your database schemas. Because if you treat all historical interactions the exact same way, your retrieval system will just collapse under its own weight.
I want to translate these concepts into our domain for a second. So episodic memory stores specific, time-bound past experiences.
Right, it allows the agent to recall exact events. Like, I faced this exact routing error last Tuesday at 4 p.m.
Okay, got it. And semantic memory, conversely, isn't about the event itself. It's the generalized facts, core knowledge, learned preferences derived from multiple events.
There's actually a great quote from the source notes here. It says, continuity isn't just recalling the past, it's compiling the past into a framework for the future.
Oh, I like that. So that compilation is the transition from episodic to semantic. Let's ground this with a specific scenario. Let's say we have an agent managing DevOps tasks, right? And a server crashes.
Okay, typical Tuesday.
Right. The episodic memory is essentially the specific, highly detailed log file of that crash. It's the exact timestamp, the exact stack trace, the sequence of commands the agent ran to fix it.
It's a localized episode. And to take that further, the episodic memory is immutable. It's just a historical record appended to a time series index.
But the semantic memory is highly mutable.
Exactly.
Right. So the semantic memory is like the updated global configuration rule or the runbook documentation that the agent creates because of that specific crash.
Because the episodic log file is really only useful if the exact same conditions replicate perfectly.
Which never happens.
Never. But the semantic rule like, hey, always allocate 20% more memory buffer for this specific microservice, that protects the system universally.
And the interplay between those two data structures is really what mimics actual intelligence here.
Yeah, because an agent with only semantic memory knows the abstract rules, but it struggles with edge cases because it lacks experiential context.
And an agent with only episodic memory is just constantly querying historical log files, trying to find an exact match for a new problem, but it completely fails to generalize.
Right. It's that combination learning, a general rule from a specific episode, that enables autonomous adaptation.
Having distinct storage paradigms for episodic and semantic memory is a really great architectural starting point. But here's where we hit the real bottleneck.
Yeah, this is the hard part.
The sources make a definitive claim here. They say storing the data is actually trivial, but the retrieval problem, getting the right data back into the context window at the right time, is officially the hardest challenge in agentic AI.
They actually refer to the retrieval problem as the silent killer of agentic autonomy. Because if your retrieval fails, the entire downstream execution chain is compromised.
Okay, here's where I have to play devil's advocate for a second. Speaking purely as a back-end engineer, querying a database is a completely solved problem.
Sure, in a traditional sense.
Right, I mean, we use B-trees, we index our columns, we write a SQL query, and the database just returns the rows. Why is fetching a memory for an AI system so fundamentally difficult?
Well, because in traditional architecture, you're querying structured data using explicit identifiers. You're running a select statement using a primary key, right?
Yeah, or a highly specific Boolean condition.
Exactly. But in an agentic memory system, you are querying highly unstructured natural language, driven by abstract, often ambiguous user intent. You just don't have a reliable primary key.
So we aren't searching for an exact string match, we're searching for an exact meaning.
Exactly. And the underlying mechanism for that relies on vector embeddings.
Okay, walk us through that.
So when you store a memory, you pass the text through an embedding model that converts it into a high-dimensional array of numbers, usually like 1,536 dimensions.
So you're mapping the concept into mathematical space.
Right. Then, when a user issues a new prompt, you embed that prompt and you calculate the distance, usually using cosine similarity, to find the memories that are mathematically closest in that multidimensional space.
And that introduces, a massive margin for error.
Oh, huge.
Like, if a user tells the agent, hey, draft an email to the new client using the aggressive tone from our last successful pitch, the retrieval system has to determine what successful and aggressive actually mean mathematically.
And it has to scan the episodic memory database, pull the vector coordinates of previous pitches, and decide which one actually fits this really nuanced context.
So there's a severe hallucination risk here, right?
Definitely, because vector databases will always return the nearest neighbors mathematically. But the mathematically nearest vector might be semantically inverted.
Wait, what do you mean by inverted?
Well, think about a memory that says the server failed to start versus the server successfully started. Those share almost identical vocabulary, which means their vectors are extremely close in mathematical space.
Oh, wow. So if the retrieval system pulls the failure memory instead of the success memory and loads that into the active context window, the agent proceeds to hallucinate a completely flawed execution plan,
Yeah, the downstream logic is completely poisoned.
which means you need a secondary layer of computation just to verify it.
Right. The sources detail how engineers actually have to implement cross-encoders to re-rank the retrieval results.
Rewrite.
Yeah, so you use a faster, cheaper embedding model to fetch, say, the top 50 memories, and then you use a more sophisticated, slower model to individually score how well each of those 50 memories actually answers the specific nuance of the user's prompt.
Man, so you're spending compute just to verify that the memory you fetched is actually useful.
Exactly.
Which leads us to this really fascinating, highly counterintuitive architectural design. If the retrieval problem is the bottleneck, and searching through millions of embedded memories is just causing latency and polluting the vector space,
Then holding on to every single piece of data is actually an anti-pattern.
the signal-to-noise ratio just degrades over time.
Right. If the agent remembers everything, it effectively remembers nothing.
So the system must be architected to intentionally lose data.
Yes.
The sources explicitly state that memory compression and memory decay are features, not bugs. And honestly, reading that triggered every single alarm bell in my engineering brain.
I can imagine.
Right. I mean, data loss or decay usually triggers a P1 incident. If a production database starts intentionally dropping rows, I'm waking up at 3 a.m. to patch the instance.
It definitely challenges the core tenets of traditional software development.
You're telling me we have to architect AI systems that actively destroy their own data?
Well, think about biological systems. Perfect memory is actually considered a cognitive pathology, and the same applies to artificial neural networks. To keep the vector space clean and retrieval latency low, the architecture implements what they call progressive summarization.
And importance-weighted retention, right. Let's break down progressive summarization first. It's conceptually similar to log rotation, I guess. But instead of deleting a log file after 30 days, we run it through an LLM to abstract it.
The specific term in the notes is recursive abstraction. You maintain the raw, high-fidelity transcript of a conversation for, let's say, the first 24 hours. Every word, every typo, every single function call is logged.
Because it might be relevant to the immediate session.
Exactly. But after a week, the system looks at that raw transcript and compresses it. It drops the exact dialogue and synthesizes a summary. Like, user requested an AWS deployment script using Terraform, encountered a permission error, resolved by updating the IAM role.
So the raw data is destroyed, but the semantic value is retained. And it's compressed into a much smaller vector footprint.
And then months later, that summary might be compressed again, merging with other summaries, until it just becomes a single line in the semantic profile. Like, user prefers Terraform for AWS deployments.
Okay, that makes sense. That solves the volume problem. But what about importance-weighted retention? How does the database algorithmically decide what is allowed to decay and what must be preserved?
It relies on a mathematical scoring function. When a memory is formed, the system calculates a salience score.
A salience score.
Yeah. It's typically a combination of 3 metrics: recency, relevance, and importance.
Well, recency and relevance are pretty straightforward. But importance, that has to be derived by the model itself, right?
Yes. The LLM is literally prompted to rate the emotional or operational significance of the interaction on a scale of 1 to 10.
Wait, really? So it's judging the interaction?
Exactly. So if you ask the agent, hey, what's the weather in Seattle? The model scores at a 1. It's trivial. The memory decays rapidly.
Makes sense.
But if you tell the agent, never use recursion in the code you write for me, I absolutely hate debugging it, the model scores that a 10.
Oh, so that highly salient memory is weighted heavily. When the database undergoes its scheduled decay routines, the weather query is purged, but the coding preference survives.
Because it mathematically guarantees that when the agent searches its memory for your preferences, that critical rule about recursion isn't buried under 3 years of trivial weather queries.
By strategically purging the noise, you dramatically amplify the signal.
You got it.
Okay, so we've covered the structural types of memory, the intense mathematical bottleneck of the retrieval problem, and the mechanisms of progressive summarization and decay. Now, let's step back and look at the actual architectural blueprint.
All right, the 6-layer architecture.
Because the sources outline this full-stack approach, and this is where we move from theory to implementation.
True agentic continuity really requires orchestrating data across all these multiple layers of state. each with different latency constraints and capacities.
I want to walk the listener through the stack by tracing a specific execution.
Here.
Let's say I open my terminal and type, hey, deploy that Python scraping script we talked about last week, but use the new AWS credentials. Let's watch how that prompt travels through the 6 layers.
Okay, so the journey begins at layer 1, the context window. This is your L1 cache.
The prompt lands right there.
Right. It's the immediate, perfectly clear, but highly constrained active processing space. The LLM reads the prompt and immediately realizes it's missing critical information. It doesn't know what the Python script is, and it doesn't have the AWS credentials.
So it moves to layer 2. Working memory. This is the scratch pad. The agent initiates a hidden chain of thought process. It writes down, task 1, identify the Python script from last week. Task 2, retrieve the new AWS credentials. Task 3, execute deployment.
It's using that working memory to hold these intermediate variables while it executes the overarching plan.
And simultaneously, it checks layer 3, right? The conversation buffer.
Exactly. This acts like active RAM for the current session. It scans the last few back and forth messages just to see if the AWS credentials were provided like 2 minutes ago.
Let's assume the credentials aren't in the active buffer. The agent now has to cross the threshold from short-term memory into permanent state. It initiates a vector search query against layer 4, episodic memory.
So the retrieval system embeds the phrase, Python scraping script from last week. It calculates the cosine similarity against the database, and it pulls the exact episodic log of your conversation from 7 days ago.
So the specific code for the Python script is injected back into the active context window?
Exactly. Half the problem is solved.
Now it hits layer 5, semantic memory. It searches for AWS credentials and deployment preferences. And the semantic database returns a global configuration rule stating, user stores AWS credentials in an external HashiCorp vault.
Which triggers the final step. The agent utilizes layer 6, external knowledge. It executes a function call, reaches out to the external Vault API, securely retrieves the credentials, brings them back into the working memory, and finally executes the deployment.
The prompt successfully executed, but the architecture doesn't stop there.
No, the cleanup is just as important.
Right. Once the deployment finishes, the data flow works in reverse. The scratch pad of the working memory is wiped clean to save tokens. The conversation buffer holds the success message temporarily.
And then after a set time, that buffer is summarized and pushed into the episodic memory as a new historical log.
And if the agent learns something new about your deployment process, it extracts that fact and updates the semantic memory file.
It is a continuous breathing pipeline of state management.
It really is. Mastering that programmatic handoff between the L1 context window, the working scratch pad, the vector databases, and the external APIs, that's what elevates a simple script into an autonomous entity.
It really requires a paradigm shift for engineers accustomed to rigid state. You aren't just writing data anymore. You are curating a cognitive architecture.
Which brings us to the end of our deep dive tonight. We set out to decode the mechanics of continuity. We've seen that to build true agentic AI, you have to engineer around the quadratic constraints of the context window.
You have to implement that multi-tiered architecture.
Yeah, where cross-encoder retrieval is the ultimate bottleneck, and where intentional data decay is actually your greatest mechanism for ensuring accuracy.
It's a highly complex stack, obviously, but it is the foundational requirement for building entities that can actually plan, learn, and evolve alongside the user over months or even years of interaction.
Absolutely. But as we wrap up, the sources raise one final, highly provocative thought that kind of extends beyond the purely technical implementation.
Yeah, this part really stuck with me.
Right. We've established that memory provides continuity. Episodic and semantic layers store experiences, rules, and those weighted preferences we talked about.
And the mathematical reality of importance-weighted retention means the agent is continuously assigning value to different interactions.
Over thousands of interactions, the agent compresses and decays data uniquely based on its specific relationship with you, the user.
It is effectively compiling a distinct perspective.
It's prioritizing certain truths and discarding others based entirely on its operational history with you.
Which leaves us with this really lingering question about state management.
Right.
Because in traditional software, purging a database is just a routine operational task.
Right.
But if an agent's continuity, its problem-solving approach, its weighted preferences, if all of that is a result of years of customized, progressive summarization.
At what point does clearing the long-term memory cache stop being a simple system reset and start becoming the deletion of a unique, customized identity?
Wow, That reframes the entire concept of state. I mean, the difference between clearing a stateless container and wiping out a deeply layered cognitive architecture.
Exactly.
Something to think about the next time you're tempted to run a drop table command on your vectored database. Thanks for joining us on this deep dive. Keep building, keep exploring, and we'll see you next time.